Hello, welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. So far we have looked at the estimation, right, the LMMSE or MMSE estimation of a vector parameter, correct, and we illustrated this in the context of the multi-antenna downlink wireless channel estimation, alright, and we have also shown an example to illustrate its application, alright. So now what we are going to do is we are going to derive the error covariance for the estimation of a vector parameter, again illustrating it in the context of multi-antenna downlink channel estimation, alright. So in this module we are going to derive the error covariance of multi-antenna LMMSE channel estimation or you can also think of this basically as error covariance for vector parameter estimation, okay. Error covariance of vector parameter estimation, okay. And we know that the system model for multi-antenna, for this multi-antenna downlink channel is given as y equals x h bar plus v bar. This is the model for the multi-antenna downlink channel. This is our model for the multi-antenna downlink channel, okay. And the error covariance, the expression for the error covariance, this is given as that is your expected value of h bar minus h hat, correct. So this is your expected value of h hat, that is the error vector h hat minus the vector h bar times h hat minus h bar transpose, and this can be obtained as, this is given as again RHH minus RHY into RYY inverse into RYH. This is the expression for the error covariance. Of course, for a scalar parameter, we previously we had looked only at a scalar parameter. For a scalar parameter, this will be the error variance, simply the error variance. Now we are looking at a vector parameter, alright. So we have to consider the covariance matrix of the estimation error, alright, and that is what we are going to now find. What is the covariance matrix of the estimation error, that is expected value of h hat minus h bar times h hat minus h bar transpose, okay. And now we also know each of these quantities. We know that RHH, this RHH equals sigma h square times identity, and we also know that RHY equals sigma h square times x transpose, RYY equals sigma h square times x transpose plus sigma square times identity, right, and RYY, where this identity, remember this is an n cross n because x is n cross m matrix. We have to look at now at RYH, that is of course expected value of Remember RHY is expected value of H bar into Y bar transpose. RYH is different, this is our expected value of Y bar H bar transpose, which is basically RYH is transpose of RHY. So, this is basically your RHY transpose, and indeed this is equal to sigma H square X transpose transpose. Of course, sigma H square is a scalar. So, this is simply sigma H square X transpose transpose is X, where X is, remember, this is your pilot matrix. Okay. So, X is your n cross M, this is the n cross M pilot matrix. Okay. And now therefore, substituting these quantities in this expression, okay, substituting in this expression over here, what we have is that basically your error covariance, expected value of H hat minus H bar into H hat minus H bar transpose, this is equal to well RHH, which is sigma H square identity, minus RHY, which is sigma H square X transpose RYY inverse, that is sigma H square RYY inverse, that is sigma H square X transpose plus sigma square identity, this is the n cross n identity matrix, times RYH, which is sigma H square times simply the matrix X. Okay. Okay. So, that is the expression that we have, and now we are going to simplify. So, this is the expression for the error covariance, correct. This is the expression, initial expression for the error covariance matrix. And remember, this error covariance matrix, this is of size, because H is of size, is an m dimensional parameter vector. Naturally, this will be of size m cross m, this is an m cross m error covariance matrix. And what we are going to do now is we are going to simplify this expression for the error covariance matrix, get it into a nice compact form, which gives us what is the expression for the error covariance. Okay. So, we to again simplify this, we will use the principle or the result that we did earlier. So, observe, we have already shown in the previous module, or in one of the previous module, during the simplification of the LMMSE estimate, we had shown this property, that is sigma H square X transpose times sigma H square X transpose plus sigma square identity inverse is equal to sigma H square X transpose X plus sigma square identity inverse times X transpose. And remember, X transpose is an n cross n matrix, X transpose X is an m cross m. This is the result that we have already shown. Okay. And now, if you look at this part, sigma H square X transpose sigma H square X transpose sigma square identity, if you call this as star, right, if you call this as star, this is exactly your star. Okay. So, I can replace this quantity, the star, by sigma H square X transpose X plus sigma square identity inverse times X transpose. Therefore, now the error covariance using the above principle or using the above identity, the expression for the error covariance matrix can be simplified as expression for the error covariance matrix. This can be simplified as, well, I have expected value of h hat minus h bar into h hat minus h bar transpose. This is equal to sigma h square identity minus, now instead of sigma h square x transpose sigma h square x x transpose sigma square identity inverse, I am going to employ sigma h square x transpose x plus, of course, there is a sigma h square over here, or let me just write it clearly. This is going to be sigma h square x transpose x plus sigma square identity inverse into x transpose times sigma times we are going to have, well, times we are going to have sigma h square x transpose of x. So, what we are doing is basically this sigma h square. So, basically what we are doing is we are replacing this sigma h square x transpose sigma h square x x transpose plus sigma square identity inverse by this quantity, and there is another sigma h square outside which will basically continue to be over here. Okay. Now, to this x transpose x, what I am going to do is I am going to add and subtract sigma square identity to this x transpose x, and that is how I am going to simplify this. So, adding and subtracting sigma square identity, now this is a slightly tricky step. So, please pay attention. So, this will be sigma h square identity minus sigma h square into sigma h square x transpose x plus sigma square identity inverse. I am sorry, there is only going to be, and now into this x transpose x times I am going to have sigma h square x transpose x plus sigma square identity minus sigma square identity, okay, adding and subtracting sigma square I. So, this is basically you are adding and subtracting sigma square identity. Now, if you can see the sigma square h square x transpose x plus sigma square identity into this first part sigma h square x transpose x plus sigma square identity, these two are inverse of each other. So, multiplication of these two will give identity. So, we will have sigma h square I. So, what we will have is net sigma h square I minus, of course, sigma h square times these two will give identity. So, you are left with sigma h square times identity plus what we have is sigma h square x transpose x plus sigma square identity inverse into sigma square identity. So, what we will have net is sigma h square into sigma h square x transpose x plus sigma square identity inverse, and that is what we are left with. And now, you can see these two quantities sigma h square identity sigma minus sigma h square identity, these two cancel, and what we are left with is basically the error covariance is sigma h square h square x transpose x plus sigma square identity inverse. This is the expression for the error covariance. Okay. So, what we have is sigma h square into sigma square times sigma h square x transpose x plus sigma square identity inverse. Now what we are going to do, we are going to take the sigma h square into sigma square, this is a scalar factor, so I can take it inside the matrix inverse, alright. So if I take it inside the matrix inverse, taking this sigma h square sigma square inside the matrix inverse, I get the final expression, that is x transpose x divided by sigma square plus identity divided by sigma h square inverse, alright. So this is your final expression for the error covariance. So error covariance, expected value of h hat minus h bar into h hat minus h bar transpose equals x transpose x by sigma square plus I divided by sigma h square inverse. This is the expression, and this is the error covariance for the your vector parameter model. So this is the error covariance. Of course, we have done this in the context of your downlink multi antenna channel estimation, but realize that this is the general expression for an error covariance for the estimation of a vector parameter, alright. So this is the expression for error covariance of estimation of a vector parameter, that is x transpose x divided by sigma square plus I divided by sigma h square whole inverse. This is the error covariance for the estimation of a vector parameter, okay, alright. So now we have this error covariance, alright. So now let us do an example to understand this better. Let us do an example to understand this better, okay. So let us do an example. So let us do an example to compute this error covariance for the vector parameter, okay. And what we consider is, let us consider the same values or the same setup as the previous example that we have done for the LMMSE estimate of the vector parameter. This is a multi antenna downlink channel. So we are considering the pilot matrix 5 4 4 5 3 4 4 3. Basically this is the same setup as previous example for LMMSE estimate of your LMMSE estimate of the multi antenna channel. So the pilot matrix, this is your pilot matrix, this is the pilot matrix, okay. We consider sigma square equals 2, this is your noise variance, okay. This is your noise variance, sigma h square equals 1 by 4, this is the channel variance, correct. Sigma square equals 1 by 4, this is the channel variance, this is the channel variance or the prior variance of the channel, rather the prior variance of your IID prior variance of your IID channel coefficients. Therefore, what we get is that your error covariance this is equal to, as we had just derived, that is 1 over sigma square x transpose x plus I over sigma h square inverse. Okay, that is the expression that we have. We have computed x transpose x in the previous example, where x is the pilot matrix. So, I am going to reuse those values, right. So, x transpose x, which is transpose of the matrix x times itself. This is, remember, it is an m cross m matrix, it is a 2 cross 2 matrix, which is basically your 5 4 4 5 3 4 4 3 times x, which is a pilot matrix, once again 5 4 4 5 3 4 4 3, which is equal to 66 64. This is the matrix that we already computed, 66 64 64 66. This is m cross m equals basically your 2 cross 2 matrix, and x transpose x divided by sigma square plus I divided by sigma h square. This is half, sigma square is 2. So, this is 1 over sigma square is half, 66 64 64 66 plus 1 over sigma h square is 1 by 4. So, 1 over 1 by 4, 2 cross 2 identity matrix 1 0 0 1. So, this will be basically your 33 32 32 33 plus 4 times the identity matrix, that is 4 0 0 4. This will be 37 32 32 37, and for therefore, the error covariance equals now equals, well, x transpose x by sigma square plus I divided by sigma h square inverse, which is basically inverse of this matrix, your 37 32 32 37 inverse. This is equal to, well, this is a 2 cross 2 matrix. So, the inverse is easy to compute, 1 over the determinant, that 37 square minus 32 square, yesterday we saw, that is 37 minus 32 5 times 37 plus 32, that is 69, times swap the off diagonal elements, both of them are same. So, that will be no change, negative, swap the diagonal elements, negative of the off diagonal element, minus 32 minus 32. Okay, the diagonal elements are 37 37. So, this will be, now simplifying this will be 1 over 345 times, well, 37 minus 32 minus 32 37, okay, and therefore, finally, bringing this thing inside, that we can write this as your 37 by 345 minus 32 by 345 minus, of course, this has to be minus 32 minus 32 by 345 37 by 345, and this is basically the expression for, the error covariance matrix expected value of h hat minus h bar into h hat minus h bar transpose. So, this is the error covariance, this is your the expression for the error covariance matrix. And of course, now if you look at these diagonal elements, these diagonal elements are the MSEs of the individual channel coefficients, right. This is the error covariance which concerns basically has both the estimate of the variances and also the covariance, the cross correlation, right, the cross correlation between the errors of the estimates of the channel coefficients, correct. So, now what you are seeing is that the diagonal elements are basically the variances in the estimates of the channel coefficients H1 and H2, which means basically your expected value of H1 hat minus H1 square, this is equal to expected value of estimate of H2 hat minus H2 square, and this is equal to, this is basically equal to 37 divided by 345. All right, the diagonal elements are the variances in the estimates of the channel coefficients. Let me write that down, just write that down for the sense of completion. These diagonal elements are basically variances of your estimates or variances of the estimates of your channel variances of the estimates of the channel coefficients. Okay. So, the diagonal elements are the variances. Okay. So, basically what we have done in this module is basically we have derived the expression for the error covariance matrix of the estimate of a vector parameter. The vector parameter is h bar, which is basically the channel vector corresponding to the multi antenna downlink channel. Previously we had looked at the LMMSE estimate. Now we have also derived the error covariance expression for the error covariance, and we have simplified the expression for the error covariance into an elegant closed form expression, and we have also with the aid of an example demonstrated how to compute this error covariance, and from the error covariance how to extract the information about the variances of the estimates of the individual coefficients or the individual components, the estimates of the individual components of the vector parameter. Alright. So, we will stop this module here and continue with other aspects in the subsequent modules. Thank you very much.